Hi, I'm Harry Nickerson, and I have retinitis pigmentosa, which is a degenerative eye condition. This project continues my previous Ingenious Plus initiative, where I developed an AI-powered retinal screening solution for smartphones. Now, I have designed and built an affordable camera using a Raspberry Pi and 3D printed components to capture detailed retinal images without pupil dilation. All plans are being released as open source to make sure this solution makes screening for retinal diseases accessible for everyone. Access to affordable, timely eye care remains a critical challenge, especially for rare retinal diseases like retinitis pigmentosa, RP, and other underdiagnosed conditions. My innovation addresses this gap by combining image classifiers with a user-friendly, portable, non-mydriatic imaging device that I personally designed. This approach empowers patients, healthcare professionals, and researchers with accessible diagnostic capabilities. At its core, my solution employs multiple image classifiers to analyze fundus photographs. One classifier verifies that the submitted image is a true retinal photo. Another assesses image quality, and additional classifiers detect a range of retinal conditions, including RP, Stargardt's disease, diabetic retinopathy, and glaucoma. This ensemble method minimizes errors and reduces false results, creating a robust diagnostic tool. I remain committed to expanding the system to detect even more retinal diseases as new data and research become available. A key innovation is the camera that I designed. It is a low-cost imaging device built using a Raspberry Pi, affordable electronics, and 3D printable components. Unlike traditional systems, this camera captures detailed images of the retina without requiring pupil dilation. It uses infrared light, or IR light, for alignment because IR does not constrict the pupil, ensuring the eye remains in its natural state. A brief flash of white light then illuminates the retina, capturing a high-quality color image. This design eliminates the need for expensive, invasive equipment, along with prescription eye drops, mydriatics, and makes the advanced retinal diagnostics accessible for everyone. Crucially, the entire solution is open source. I am releasing all design files, source code, and research documentation freely, inviting innovators, researchers, and healthcare professionals worldwide to use, improve, and extend the technology. By fostering a collaborative, open community, I aim to accelerate research into retinal diseases and drive continuous improvements in diagnostic accuracy, ensuring that this solution remains accessible to all. Driven by personal experience with RP and the transformative power of early diagnosis, this project not only benefits those facing barriers to traditional eye care, but also serves as a platform for ongoing research. By sharing my work openly, I hope to spur further advancements in retinal screening and expand the range of detectable conditions, ultimately improving eye care on a global scale. Personal and familial experiences with RP inspired me to create a more accessible diagnostic solution. After my own diagnosis and witnessing my mother's prolonged misdiagnosis, I researched the key indicators of RP, discovering that bone spicules in retinal images are a critical diagnostic marker. This insight led to the development of an AI-powered screening system. I engineered a series of specialized classifiers. One confirms a valid fundus photograph, another evaluates image quality, and additional classifiers detect RP alongside other retinal diseases. This multi-step approach increases accuracy while reducing false positives. Recognizing that traditional retinal imaging is expensive and inaccessible for many, I designed my own low-cost camera. Anyone with a 3D printer could build this device using a Raspberry Pi and affordable components. The camera uses IR light for alignment, since IR does not constrict the pupil, followed by a quick flash of white light to illuminate the retina and capture a high-quality color image. Importantly, I am releasing the entire project as open source to invite the global community to contribute to ongoing research and expand its capabilities. My research and design process is deeply rooted in personal experience and collaboration with experts. I began by reviewing academic literature on RP and retinal imaging, which underscored the importance of early detection and highlighted the limitations of traditional hospital-based systems. Working closely with retinal imaging specialists Dr. Robitaille and Dr. Smith from Dow University and the IWK Hospital provided detailed clinical perspectives that informed my design choices and validated key diagnostic criteria. These experts helped me refine imaging parameters necessary for accurate AI screening. Additionally, partnerships with organizations like Fighting Blindness Canada enabled access to a diverse dataset of fundus images for training robust AI classifiers. Consultations with optical engineering specialists were also critical. Their recommendations led me to adopt infrared light for alignment because it does not cause pupil constriction, and a brief white light flash for high-quality color imaging. Though iterative prototyping and feedback from these experts, I honed both hardware and software components. Embracing an open-source community development model, I invite the global community to contribute, ensuring that the process evolves and remains at the cutting edge of retinal diagnostics. My innovation benefits individuals facing barriers to traditional eye care, such as those in remote or underserved areas, people with limited financial resources, and patients with mobility challenges. It empowers patients to conduct early, accurate retinal screening at home and offers healthcare providers a rapid, accessible diagnostic tool. Moreover, as an open-source project, it serves as a research platform for scientists and clinicians globally, facilitating collaborative advancements in retinal disease detection. Ultimately, this project aims to improve outcomes for individuals at risk of vision loss and drive ongoing innovation in eye care. Currently, retinal screening relies on expensive hospital-based fundus cameras and specialist evaluations, methods that are inaccessible to many communities. While portable cameras exist, their high costs and limited diagnostic capabilities hinder widespread use. In contrast, my project integrates AI-powered diagnostics with a DIY 3D printable camera built from affordable components. By releasing the solution as open source and collaborating with retinal imaging specialists Dr. Robitaille and Dr. Smith, I offer a research-driven platform that anyone can use and improve upon. This approach democratizes access to advanced eye care and fosters continuous community-led innovation. One significant challenge is obtaining regulatory approval from Health Canada, which may delay widespread use. Additionally, ensuring the consistent quality of low-cost components and encouraging adoption of a DIY approach could pose hurdles. However, these challenges are mitigated by the open-source nature of the project, which invites community contributions and iterative improvements. By collaborating with regulatory experts, establishing partnerships with reliable suppliers, and sharing comprehensive build instructions and research openly, I aim to overcome these barriers. Ongoing input from experts like Dr. Robitaille and Dr. Smith further strengthens the technical and clinical foundation, building trust among users and researchers alike. Collaboration has been pivotal in the development of this innovation. Early on, I partnered with Fighting Blindness Canada, which connected me with iCar CNR and provided a comprehensive dataset of retinal images essential for training my image classifiers. In addition to clinical partners, I consulted with optical engineering experts to perfect the camera design. Their recommendations on lens selection and lighting configurations were vital in creating an effective, accessible device. The announcement of an open-source release of this project has already spurred global interest, ensuring that further contributions and improvements continue to advance this research-driven solution. The cash award would serve as a catalyst for further research and development, ensuring that the solution remains accessible and continuously improves through community collaboration. A portion of the funds will be dedicated to expanding the AI algorithms, gathering more data and training classifiers to enhance accuracy across multiple retinal conditions, including RP, Stargardt's, diabetic retinopathy, and glaucoma. This will reduce false positives and support ongoing research. Another significant investment will be in refining the camera I designed. Funds will be used to source high-quality, affordable components and optimize the build process so that anyone with a 3D printer can reliably assemble the device. Gathering real-world feedback will allow iterative improvements that will be shared openly with the community. Additionally, part of the award will support the creation of comprehensive documentation, online resources, and open forums to facilitate knowledge, exchange, and collaboration. Rather than focusing on commercial market adoption, the primary goal is to advance research and make this diagnostic tool freely available to any community or researcher interested in improving retinal care. This approach embodies the spirit of open innovation and shared scientific progress. I want to thank Ingenious Plus and the Rideau Hall Foundation for supporting my research so far and allowing me to share my project with the world.